let us start with this objective problem. इसको क्या करना है? ऊपर हटाने के लिए. अच्छा. Hide video panel. A floating meeting. Yeah. So let's look at question number 10.
चल ठीक है बाय.
Read this question carefully. There is a
अभी क्लास है ना नंगा.
conducting ball. There is an uncharged conducting ball of radius r. This ball is earthed with the help of an inductor of inductance cell, right? At t is equal to 0, there is no charge anywhere. And now there is a electron beam of number density. If you look into it, the number density of the electron beam is given, n, and they are all moving with a constant speed of v. So this electron beam is bombarded on the conducting sphere. Now, the point is, we need to understand that at t is equal to t, if the charge on this conductor is q, how is this charge varying? And that is where the answer to the question lies. There are two things in this problem. I need to understand what is happening with q. So what exactly is q as function of time? And also I need to understand that if the current coming from the earth, they can be negative also. So if I'm assuming this current to be I, what is the maximum current through the inductor? So basically our interest is I as function of time and q as function of time. I've assumed some direction, right? Now, as far as the electromagnetic term is concerned, we understand as I will pass through the inductor, inductor will oppose it with the EMF, which is L di by dt. So this is the induced EMF in the inductor by Faraday's law. Other than that, the rate of change of Q, so basically dQ term by dt, that is because of the current which is coming from this line, from the earthing line. So I as function of time. Also, because this beam is getting bombarded on the hemispherical section, so the total current which is reaching the surface, if I draw a disk of area pi r square by NEAVD, I can say the total current which is entering from this side, actually negative charge is entering from this side, so practically current is leaving. So it is coming from this side minus it is leaving, which is same as the electronic charge which is coming. So it is N, what it is? So it is A term is pi r square, multiply this term by V. This is our equation number 1 in the problem, right? And secondly, one equation I want to write by KVL again in this problem. Observe this carefully. I will treat this problem as a combination of a inductor and a capacitor. It's actually a LC circuit. That's why the results will also be oscillating. So practically it is a problem of LC oscillation, because if you look into this surface, right, from this point, again I'm presuming that this sphere is forming a capacitor with infinity, right? It's forming a capacitance with infinity, and that guy again is at 0. So basically 0. I want to write the net potential drop from this point till infinity by KVL. So my term here is L di by dt. That term is there, right? And some q by c term. So plus q as function of time by capacitance between this r and infinity, and that is 4 pi epsilon naught into small r. So practically we have got these two equations, right? Now things seem fine. So I'm not writing as function of time again and again. I will just substitute d by dt of q term. But q term is minus 4 pi epsilon naught L R di by dt, right? And that term will be equal to I minus n e pi r square v. Now observe this carefully. So basically, effectively what I am getting, I'll write that as final equation downside here. I'll have d2I by dt2 term, right? That coefficient I am having as minus 4 pi epsilon naught LR, and RHS I am having I minus n e pi r square v. This complete expression is a constant. So it is more of, let me just directly write this equation. It seems like it is d2I by dt2 is equal to minus omega square x, and seems like it is I minus plus some constant. So treat that term again as I, it doesn't matter. You're getting the term, no? It is minus omega square I plus some constant, keep that constant as k, forget it. So now a lot of things are clear in this problem. Remember, what is my omega now? Omega square term I'm getting as, what is that term that I'm getting? 1 upon 4 pi epsilon naught LR. Yeah, 1 upon 4 pi epsilon naught L into R. Fine. I think all of us understand that I'll redefine my current reference, and then it becomes an oscillatory term. You got this equation correctly. What is that constant coming out as? You write it as minus omega square. What is the term we are getting there? Is I minus omega square I term is there, then plus, so minus again, and some, I prime, I may say, I. All good up to this stage. I is a function of time. So tell me what is the result we are getting. I'm directly writing my answer. My I minus I prime, that I prime is again a constant term. This term is a constant, and that I am getting upon as some constant I double prime into sine omega t plus phi. He is talking about all the parameters. I mean, just try to look into this problem in a subjective way. As far as the answers to the problem are concerned, we can write from that equation directly. But I want all the parameters to be individually sorted in the problem. Agar current ka function I have to write, charge function, each and everything we can find out. Just observe everything in that equation. I prime you know now. Omega is already known to us. I double prime and phi, these can be eliminated now. At t is equal to 0, I should have been 0. So I know that minus I prime is I double prime sine phi. So I have this fifth equation because at t is equal to 0, the current through the inductor was 0. Now what is the only variable which is left? I double prime and phi make equation or chahiye. One more equation is required, sixth we can say. And let us look into the potential drop at t is equal to 0. So initially there was no charge. So even L, the equation that you have written here is this. So di by dt is also 0 at t is equal to 0, but t is equal to 0, there was no charge. So take the derivative and make it equal to 0. So basically, I double prime omega cos omega t plus phi. So cos phi, that comes out as 0. So practically your phi becomes pi by 2. And now everything falls in place. And I double prime becomes minus I prime. I think your I equation is very much known to you. And as far as the charge is concerned, because I is known, so Q is also known. So he's talking about the maximum charge. So when Q term is maximized, di by dt term is maximum. I think you can also write Q as function of time. So calculations apart now, conceptually, I think the problem should be known. You can solve this now. Fine. Okay, so let us move on to the second question. I am leaving the calculations to all of you now. Q and I functions, we should be able to solve at this station. And this differential equation which I have written here, I think you understand. I am writing it with respect to I, then I have changed it with respect to I minus I prime. So that is one and the same. Next. So let's pick second question for the day. Now, in this problem, again, based on inductance, he has actually generated a fresh idea. So let's try to understand the idea and the problem. First of all, I'll give you the conventional answer and then I will explain what does the problem want. The question is somewhat like this, that there is a ring having a mean radius of small r and cross-sectional area A. So basically, this is our ring, radius small r, the cross-sectional area here is given as A. So conventionally what he has done is, there is a magnetic field in the room and somebody has placed a conducting ring there. The question was that if I flip this ring and make it vertical, let's say I put my, any ring on a table and rotate its plane by 90 degrees. So then all the field lines will be normal to it. And I position it there itself. So, think like that I will bring it back into the YZ plane and I will keep it there. The question is, if you keep the ring there in the YZ plane, what is the current in the ring after it is turned through an angle of 90 degrees? Now, the conventional thought is, if nothing would have been given in this problem, then a student will say, fine, the initial flux, whatever is the flux. So while you were changing, fine, the current will be generated. But once the ring is there in this plane and you are holding it, whatever B is going, that will provide a flux, but that will remain constant with time. So if flux is constant, no EMF can be induced. So there is no point of current, so answer is 0, which is actually the wrong answer. So let's understand what he wants in this problem. That is where the question is different from conventional problems. He says, let me explain. So ring ka mean radiuses are the cross-sectional area capital A, perfectly conducting wire. The inductance of the ring is small. Now, why he is giving all this? He is saying inertia of free electrons cannot be neglected in the current building process. Generally, we neglect it. But he is saying in this question, presume that you cannot neglect the inertia of free electrons. And a lot of things are given. The free electron density is small n, the mass of electron m, the charge on the electron E, and these are the informations given. Now just think from the basic. The problem is, when you position it normal to the magnetic field, if B was prevalent, if B comes into picture, then B brings a flux of B into pi r square. Let me say something conventional. And to counter this, because it is a conducting, like a superconductor kind of stuff, no resistance is given. So this would have generated a I, where I would have been this divided by inductance. Now the problem in this question is self-inductance is given, yeah, inductance is given. This is what I'm trying to say. I'm saying if you have a superconductor and you try to bombard, because flux through this zero resistance ring will be constant. So if you bombard some flux through it, whatever change you are bombarding, it will generate a current of its own. It will negate the change. So Li term will be equal to B into pi r square. This happens in conventional bodies having zero resistance in electromagnetic induction. But in this problem, this equation is not going to work. Rather, you have to define something called upon as, pseudo inductance, you can say L prime. So if you want to make this equation correct, you have to define a pseudo self-inductance type of term, which is because of the inertia, the consideration of inertia of those electrons. Now, let us leave this problem for a moment and think about that consideration. What will happen? Now, if let me take this kind of ring and let me provide it some current. Now, if there was some current I and you want to change it by di, you understand that the energy that we are looking into is kind of half Li square. But this energy should be compensated in such a system with the kinetic energy of those electrons, which we generally neglect. What I'm trying to say is, by conservation of energy, what basically Faraday's law of electromagnetic induction, we are talking about conservation. So by conservation, what we are trying to say, if because of those electrons there is some pseudo inductance, and that I'm calling upon as L prime, then whenever I will write the energy in the current of that pseudo inductance as half Li square, it is actually one and the same as saying, actually there's nothing, but I will write kinetic energy term as a inductance term. That's why I'm explaining this. And that will be this half m into v square. I have to take the total mass of all the free electrons. And that will be mass of one electron into number of such people. The number of such people in this volume will be number density n into volume. And volume will be A into 2 pi small r. Right? So this half will cancel out. Your L prime will come out as m n a 2 pi r v square upon I square. But what is I? It is n e a v d. If they will start moving with v in that ring, the current that will be generated is actually NEAVD. So it is NEAV. So if you look into it, V square term will cancel. So MNA 2 pi R divided by N square, E square, A square. So N term is compensated, A cap area is also compensated here. So I think now it is simple. It is m into 2 pi smaller and divided by, just be careful, n e square a. Just check all the terms carefully. Are you getting this expression? 2 pi r m upon n e square a. And that means if I want to solve this question, the answer to the problem should be the flux compensatory term, the b pi r square term upon inductance, which is originally present, self, and because of this inertia term, additional inductance, which is m 2 pi small r upon n e square a. The final result to the problem will be this. I'll explain it again. And let me clarify this point that all the questions that we are solving in inductance, actually this phenomena is always present because you cannot neglect those electronic charges as inertial as people. But under the approximation that we are neglecting such terms, we are writing our expressions. In this problem, that is what he wanted us to analyze. So you have to precisely write the net self-inductance, and this is the additional pseudo self-inductance. Actual inductance है वैसे ये, but it is apparently defined with the help of this energy term, which I am writing as kinetic energy, which I am trying to relate with this term. Oh, होगा ही होगा, because if you are talking about current and you are talking about an energy which is there because of current, that energy is actually because of velocity of free electrons. That is what we are writing. That is the additional inductance. Test everything remains as such, you'll get yours. Right? Let us pick up the third problem for the day. Okay, so let me take one problem which is fundamental and based on absolutely basic calculations of LCR circuit without any AC input. This is a standard combination, a circuit which comprises of a resistor, an inductor, and a capacitor. There is no input given, but the signal, the current charges in the circuit are electromagnetically oscillating. Now the question is, so it is more of a damped oscillation kind of problem. The problem comprising of R, I have got a L, I will have a C, and this is the input. This circuit is LCR series, no input. Okay, एक बार initiate हो गया, now it is moving. Now what he is trying to say is, he wants to analyze this problem from an initial state to a final state, just a conceptual idea, to a final state. And he knows that the damped oscillation which is happening, so whatever is I in this circuit, as it is exhibiting a damped oscillation, damped SHM, so he's saying the amplitude of current through the resistance is dropping from I to 0.5 I. And in this tenure, can we write the amount of heat dissipated? So what I'm trying to say is, try to analyze the initial state where the amp of the current itself is capital I. Just let us try to analyze it at that instance. If that is the case, at that instance, LDI by dt term will be 0. Maximum hai current ka. So that is gone. And because I have this current I, the amplitude term here, plus minus. So let me write some minus plus, and there will be some charge plus Q1 and minus Q1 here. So I think we understand that Q1 upon C is being balanced by IR because this term is 0. Right? So technically, while I'm writing the answer to the question, what I would have thought is the amount of delta H that you want to eliminate as heat from the resistor should be the total decay in the potential energy of the system. And that energy is in two people. So basically, initially I have got, I'll use the same idea. So I have got a half Li square term and I have got a half Q1 square upon C. So that is half of, R square I square C. Just check that. Half C square से भी लिख सकते हैं. And simply I would have written that in the final state, Naya amplitude is I by 2, so we could have taken half L this term and simply half CV square, and V seems more practically I by 2 into R, this term ka whole square. Just take the difference of these two terms, you should get your result. So LCR series, such kind of things they can do directly by conservation of energy. So you'll get your result, right? Okay, now let me take a combination where he is talking about change of flux and he is attaching mechanical motion also in the problem. Just observe it carefully. These are the three segments to the same problem. Observe the information carefully before we answer the question. Let's understand what is happening in the problem. There is this thin ring here. Okay. इसका radius R0 है. And gravity is present in the problem. G is present. So there is a cylindrical bar magnet which is kept downside. and the magnetic field lines of the bar magnet, like that of a ring, are fanning out, right? And on the axis of that cylindrical bar magnet, I have kept a small ring. Now, the mass of the ring is given m. The radius of the ring is also given, that is r naught. Mass is given, radius. There is no resistance in the ring. So again, we have to be careful. No resistance. Now, the magnetic field which is present there, Bz, try to understand it is B naught into 1 minus alpha z. So, I mean, this point he has considered as, somewhere here as, z is equal to 0 position. So, as you are coming down, the vertical magnetic field is increasing as expected. And there is a radial magnetic field also. Okay? तो जो B का रेडियल कंपोनेंट है दैट इज सम B नॉट बीटा R. Now the question is, all the informations are given here. This is BR, this vertical is BZ. Now initially the ring carries no current. The question is, if the ring is released and it starts to move down from the axis, preserving its vertical axis, what are the statements we can make? And initial coordinate of center of ring is given. You have to neglect the resistance, and L is the self-inductance of the capital resistor. So let us think step by step. Now, as you drop that ring, because of G, it will start coming down, and as it starts coming down, the flux, because the radial magnetic field will not generate any flux across the ring, but the axial magnetic field will have some flux which will increase as you come down. So if I look into the top view, from top view, if I observe the ring, it seems that it will have a clockwise induced EMF. क्योंकि जब flux नीचे से ऊपर बढ़ रहा है, तो it will have a clockwise induced EMF from top, so there will be a EMF. And because this EMF will, I'll write the expression of this EMF. As this EMF will try to generate some current in this ring, because the ring has got a self-inductance, the self-inductance of the ring will oppose that by a term which is L di by dt, self-inductance into di by L di by dt term will be. So, because there is no resistance in this ring, so by KVL L di by dt term is this. So the complete concern that I have got right now is to write that mutual EMF term, mutual induced EMF term. So let's see what is the term we are going to write here. So simply I'm interested in d phi by dt. So what I would have done is that Bz, now try to observe that Bz term only. That Bz is B naught into 1 minus alpha Z. Z term there is negative, right? So as you are moving down, it is kind of plus Z mod kind of term. So this is increasing. So I need d phi by dt term, simple. So my area for the ring will become pi r naught square, and simply I'm interested in d by dt of this term. So that is B naught into alpha into V. So if at this instance t is equal to t, it is down here and it is acquired a velocity V at t is equal to t, this is the term that I would have d by dt of that term. This is a variable term, right? और ये आ गया L di by dt term. I don't know what is I right now, but I am clear that pi r naught square B naught alpha into velocity at this instance is actually L di by dt. That is my first equation. Remember, we are very categorically, V is the speed here, treat it as speed. So I'm treating this V term as positive. So V dt is the distance that it is traveling downwards. So basically the current that you can see, I term which will be there in the system, that will be in terms of the Z parameter. So technically, I should say that I should be equal to pi r naught square b naught alpha by L into VDT. And that VDT term integral, so that is actually Z mod. So if I have traveled Z downward, yeah, Z mod downward, this is the amount of current which will be there in the ring, and it will be clockwise, and it will be clockwise. So fine. I mean, by this equation, I understand what is current as a function of the distance that I have traveled downwards, Z mod. Now, the second thing. So this is for Z in the downside direction, Z in the downward direction, right? Now, what will happen as the current will come in the ring? First, the ring will start dropping. As it will drop, the flux will increase. To negate that rate of increase, there will be a clockwise current. And as the clockwise current come, it will interact with the radial magnetic field. So ये current जो आएगा, this will interact with this radial magnetic field which is present there. And the interaction of current with the radial magnetic field, look into the forces I L cross B, it is coming out. And this is a top view. So there will be a magnetic force coming out, which should be current into 2 pi r naught into B as function of R. And that B is B naught beta r naught. Be very careful what I have written. I have written Fm is equal to I 2 pi r naught into B, and B is B naught beta r naught. This is the expression of magnetic force. Remember, it depends upon I, and I depends upon Z mod. Now, it is easy because if I look into the force equation at T is equal to T, which is also the general position, what is the equation I'm getting? There is a mg acting. So, अंदर की तरफ है इस diagram में mg on the ring downward, and according to this diagram there is mg here, and there is this Fm which is acting like this. That's what I am saying. So I'm having a mg term and minus that Fm term. Now we have to solve it carefully. Minus, it comes out as 2 pi r naught square beta b naught into I. And I, let me write as, again, big expression. So pi r naught square b naught alpha upon L Z mod. That is fine, all good. And that should be mass into acceleration. So that is d2 Z mod by dt2. Because Z mod is the distance I have traveled downwards. So downward acceleration is, downward I have taken as positive also. So d2 Z mod by dt2. And now you can observe this equation carefully. SHM. Again, it is constant minus constant into Z mod is constant into second derivative of Z mod. So in Z mod, it will oscillate. I could have written this for Z also, doesn't matter, but so negative tha. I don't want it to confuse you. That's why I've taken this. Now we can answer the questions. Let's see. First part. There is no current in the ring while it is in motion, no? In fact, in Z is an oscillatory function, na? Z mod is sinusoidal. And Z mod and I are proportional. So I is also sinusoidal. No current is not right. Net EMF induced is induced in the ring while it is, no, that is not right. Because there are two EMFs which are induced. First, which are because of mutual inductance, because this ring was falling in the external magnetic flux. और उसकी वजह से जो current आया उससे internal आ गया. And these two terms are cancelling. So net induced EMF is 0. Net magnetic flux is through the ring is constant at every instance. That seems right because that is actually 0. I mean, whatever it is, at t is equal to 0, whatever it was, that will remain constant. Because whatever flux will change because of this dz, as I move down, LdI over dt is compensating it. Li is also that additional flux, na? So net flux is constant. That is perfectly fine. Zero non-zero doesn't matter. It is constant. And variable galat hai, so that's not possible. And now comes the more calculative part. So he said the net magnetic force in the ring, and he has given these answers as function of z. So you may write as z mod. है ना? वैसे तो इसे लिखना चाहिए था net magnetic force upwards, and this is z mod because z is negative downward. So think in terms of z mod, and which term he is interested in? Is interested in this Fm term, basically this term 2 pi r. So I think A option seems correct. Just if you just observe this expression here, this matches with this expression which is given. And finally, he said, what is the ring doing? It is executing SHM about its initial position as equilibrium. That does not seem correct. Initial position can't be equilibrium because velocity is zero. So that is the extreme position. है ना? कहीं और ही आएगा equilibrium. वैसे भी for equilibrium this complete LHS is zero, na? So Z mod can't be zero. It will have some non-zero. So ring executes periodic. Initial, again wrong. Initial is equilibrium, not right. So now the only thing was to check what is the angular frequency. I think you just divide this equation by m and look into the coefficient of Z mod. That should be your omega square. So that 2 should be there. So I mean C should be correct and D should not be the correct result. You got it, na? Acceleration wala term dekh raha hu. So divide it by m and look into the coefficient of minus Z mod after dividing by m. That coefficient is omega square. So you will get your angular frequency in the top. Okay, let us move on to the next problem for the day. Now let me take this problem where not very calculative. Just observe the situation carefully. The problem was like this, that there is a mass, there's a ring of mass m and radius capital R, and it is set into pure rolling on a rough horizontal surface. So it's given. And basically he has provided a V and omega and V is equal to R omega. So rough surface पे roll करके छोड़ दिया. And you know, there is a point charge Q which is fixed on the ring. Q कहीं पर fixed था. Now the question is, if friction is sufficient so that it does not slip at any point of its motion, theta वगैरह दिया हुआ है, what exactly is going to happen? And remember that charge which is fixed on the ring does not have any mass. Think about it. The charge which is given on the ring does not have any mass. Got it? यहाँ तक ठीक है? Now, which positions we should be concerned about? यही दिमाग में आ रहा है ना? So the thing is, in such a problem, it is better. Now the thing is, I could have analyzed this problem with respect to the center of mass also, because remember this problem will become even more interesting if I give mass to that charge also, because then the center of mass will shift and then it will be real good analysis. So you will take that problem as an extension. What I wanted in this problem, let me repeat. This question is still simple because there I have given a ring which has got uniform mass distribution, and a point charge is fixed at the highest point without any mass. और उसको pure roll करके छोड़ दिया. Now you have to analyze what are the conditions, what is the friction. So if friction is sufficient enough for it not to slip, let's see what we should write. So let me first analyze it. What I'm trying to say is, maybe I left it from this point in the beginning when it was here. I would have given it V naught and I would have given it omega naught. Maybe I started from this point at t is equal to 0 and omega naught was V naught by R. Right? That was fine. Then let's see what happened. So from the diagram, it seems that when it reached this position, theta, the center of mass acquired some V, it acquired some omega. Omega is actually V by R. And there is a charged particle here. Center of mass is still there. It is still rolling. So I've just taken this condition. Now, let me analyze the dynamics of the problem. So, what are the forces? I have got a mg. I have got a normal reaction here. I have this charge q here. Now I want to take the magnetic force on the charge. So, practically, the thing is, it's better to use ICOR from here. And let me use this as my net velocity. And because this angle is theta, so these two angles are theta by 2. This angle here is also theta by 2. So the velocity he will have is what? It is r, 2r. So 2r cos theta by 2 multiplied by omega. That is the velocity. And remember, capital R omega is V at this instance. So 2V cos theta by 2 is the velocity in this direction, which is normal to the line connecting the ICO. So I will directly write QV cross B instead of taking those two velocities separately. Simple. So QV cross B now. And this V cross B will be directed in this direction only. Right. So now things are simple. So it is Q2V cos theta by 2 multiplied by that term, which is B. Here, this much is fine. Now let me analyze the forces. So mg I have got, n I have got, this force I have got. And it is passing from this point only. This thing justifies the fact that alpha about ICOR, because torque is 0. So alpha is also 0. So ACM should also be 0. So V will be equal to V naught. And omega will also be equal to omega naught. This is the sequence of events. Right? I started with V naught and omega naught. And as it moved forward, I thought it is rolling, but it may change the speed and omega. But when I analyzed, this magnetic force is not providing any torque about the ICOR. So alpha was 0 from there. Then I was clear. So alpha is 0 every time. That means ACM is also 0. So V cannot change, V and omega same. So that's why he was clear that whatever is V and omega is same as that of the beginning. So let's not confuse with V or V naught, omega, omega naught, same. So let's come back to the question. Now I want to write the value of normal reaction and friction, two things. So because ACM is 0, as ACM is 0, I should have said that the friction will act leftwards, Fs. That will be balancing the forward component of this force. Right? So this angle here, what is this angle here? With the vertical, it is theta by 2. So this is 90 minus theta by 2. So the cos component, so my friction acting leftwards will be 2qvb cos theta by 2 term and cos of 90 minus theta by 2 sin theta by 2. Whichever way, it is basically qvb sin theta. Just observe, it is qvb sin theta. This much friction will act. So this seems correct, C option. It may be multi-correct, so let's be careful. Stay with the problem. And what about N? This is the vertical component. So this will be how much? It is 2, what will be that? 2qvb cos square theta by 2. 2qvb cos square theta by 2. Again, I'm writing V always is V naught. And omega always is omega naught, and V naught is already R omega naught. So this is something we are known with. Now, so now there is a hassle that we should ensure everything is fine. It will keep on moving with the same V and omega. We should ensure that it does not lift from the surface. So the point is, at the highest point, let's understand the value. I mean, this value is not exactly equal to. I mean, what I wanted to say was, it has got a vertical component, and mg minus this. So basically, it is mg minus this. You know, normal reaction is balancing by this. So practically, my interest was this person is having the highest value at the highest point. So there, the normal reaction is least. So when the charge is at the highest point, the normal reaction is least. And if the ring does not lift at that point, it will not lift anytime, ever. So basically, you understand, put theta is equal to 0. So mg upon 2qb. So will lose contact with the ground if V is greater than this. So we need to ensure that the least normal reaction is also greater, and least normal reaction is mg minus 2qvb. So you understand that V should be less than equal to mg upon 2qb. So, I mean, if it is greater, it will lose contact, is fine. More options. B is obviously wrong. A, the ring will continue to move with constant velocity for the case when it does not lose contact. So A, C, and D options are. So my suggestion is, when you are solving such problems, and problem with angular impulse, linear impulse, or some rotational idea, they are definitely probable ideas for the JEE paper, right? Let us take up the next problem for the day. Now, just an extension to that problem, I'll come to it. If I can just take a small problem again, which is based on interaction between magnetic dipoles. So, and along with electromagnetic induction. Just read this. So, lot of theoretical concepts are there in this problem. Actually, he gave a small magnet, a bar magnet. So there is this small magnet here, and it is moving with a constant velocity v towards a fixed conducting ring of radius a. So this guy has got a radius of a, YZ plane. Now, the electrical resistance, note everything carefully. The resistance of this ring is given capital R, right? Self-inductance is vanishingly small. Uska L to 0 ही दे दिया. फायदा हो जाएगा इससे. Analysis becomes a bit easy. So no self-inductance. And he's saying this bar magnet can be modeled. We understand this is like a magnetic moment, small m, या mu m, या pm, whatever it is. So ये बताना है that, and your answer will contain this coordinate. Remember, your answer will come in terms of position. So if I am at a distance x right now from the ring, and somebody is ensuring that this dipole, this bar magnet, keeps on moving with a constant velocity v, then what is the force that agent is exerting on the magnet? एक ही बात है. What is the force of interaction between the bar magnet and the ring? So the same is applied by the agent, because it is moving with constant velocity, and this ring is also held fixed. This is the problem. Now let's see how we analyze this combination. So what we should do in this problem? My idea is तीन चार steps, and just listen to the steps and then you have to solve. First of all, the bar magnet will move towards the ring. So because of magnetic flux, magnetic field lines generated by the bar magnet, the flux will pass through the bigger ring. Now, as this bar magnet approaches close, the flux starts changing. So the first step is to write the flux. because of magnet through the ring. Now, because of his motion, the flux will change, the field line pattern will change. So, because of rate of change of flux, induced current will come, induced EMF will come. That induced EMF will generate an induced current. Now, that induced current will generate a magnetic field, which will come back to the magnetic moment. And that magnetic field, along with magnetic moment, will have an interaction energy minus mu dot B. And when he will move, there will be rate of change of that interaction energy, and that is the answer. Minus mu dot B ka dy dx. So that is how we will go about solving this. A lot of calculations. I'll try to write few equations. Now the first step is, let me write the flux. Phi. So flux के लिए भी एक और theorem use करना पड़ेगा. I'll use reciprocity theorem. What is reciprocity? The point is, I mean, there are two ways. One way is I can write the magnetic field at all the points. So मैं इसके अंदर जाऊँ, I cut an element, I write magnetic field because of dipole, and then that component of magnetic field which is normal to it will provide flux. I integrate, I get my answer. That is one way. But the easier way, there are two methods to write this. I'm using the easier method, the reciprocity wala trika. उसमें क्या होता है? If you give this guy, I mean, if I say that M is being, simulated with the help of a small ring of radius of current I naught, radius R naught, that magnetic moment is basically I naught into pi R naught square. है ना, ऐसे ही कुछ है. ये भी तो कोई current carrying ring ही है. Now, if I want to write flux here, reciprocity says that इसमें current I am writing flux through this guy is same as the current in that person I naught and flux through this guy. So flux that I want to write, so I will presume that this I naught is here and this area, this radius is R naught, it is small also. So then the magnetic field is simple because of a ring at this point, that is mu naught into I naught into radius ka square upon twice of a square plus x square raised to the power 3 by 2 and multiplied with the area of that small ring here, R naught. And then I will say this is all a way of finding out flux. So I naught into pi R naught square is actually small m. So basically mu naught a square small m upon twice of a square plus x square raised to the power 3 by 2. This is the flux because of magnet through the ring, bigger ring. Flux through the ring because of the bar magnet. समझ गए? Now things are in place because x is decreasing, so the flux will increase. So I mean, if I am, उसने बोला नहीं था, I have assumed some direction of magnetic moment, so the flux will increase as I will move forward. So I mean, I have an induced current which will generate a flux in the reverse direction. So according to a person sitting here, the induced current in the ring should be anti-clockwise. So according to the person, there will be a I induced and that should be counterclockwise. I'm writing everything with respect to this person and that will be equal to d by dt of this term divided by resistance. So 1 upon R into d by dt of this term. So it is mu naught a square m upon 2 d by dt of this. So I'll have a square plus x square cube, right? And then all the steps. So denominator a square, what is that? What I should have written is minus 3 by 2, minus 3 by 2 minus 1, 5 by 2. So I think in the denominator I'll have 5 by 2 term. I'll have a minus 3 by 2. Anything else? 2x, yeah. And take mod of that term simply. So take a 2x term and take mod. Just check. 1 by R अलग से कर दिया, mu naught a square m upon 2 कर दिया. 3 by 2 term is there. A square plus x square minus 5 by 2, that's perfect. And 2x, perfect. So 2, 2. So basically, induced current is ready now. It is 3 mu naught a square small m x upon twice of R. Just check the calculations carefully. A square plus x square raised to the power 5 by 2. इतना तो induced current आ गया as a function of, and again I have done d by dx. So I should multiply it by v also. Multiply it by, because I had to take d by dt now. So I've written d by dx. So there is a velocity term also. And after taking mod, that all minus plus will be taken care of. This is the magnitude of the current. ठीक बात है ना? अब now the question is that at this x, this guy is having current. Now his current, which is counter clock, will generate a B here at the position of bar magnet. In the opposite direction, a B will be generated. And that will help me write U, interaction energy between my dipole and my friend's magnetic field, which is minus mu dot B. So basically this U is minus small m into B. Now what is the B that will be generated? Because of this I induced, the B that he will generate here, B, is actually mu naught into I induced into radius square, right? Mu naught into I induced into radius square upon twice of a square plus x square raised to the power 3 by 2. 3 by 2. So minus, this is mu naught, this is a square, this is twice of a square plus x square raised to the power 3 by 2 into I induced, and you have to take all this there. So 3 mu naught a square m x v upon twice of capital R into a square plus x square raised to the power 5 by 2. This is the expression of U. Still one step is left. It's a huge expression. Write it properly. U का term ठीक से लिखो. And technically, my answer should be minus dou u by dou x, minus dou u by dou. So let me do one thing. While writing the answer, I am saying the magnitude is minus dou u by dou x mod, right? And direction we can say logically also. The direction we can definitely write directly, because, you know, think of this as two dipoles. So it's like dipole moment rightward and that will have leftward. So like the question now is that if he has got a dipole moment right and he has got a dipole moment left and he is trying to move right, what is the force of interaction between them? Because that is also behaving like a dipole. So practically when you write the term, the U comes out as negative and the distance is in the denominator, na? Main observation if you do. So as you will try to decrease the distance, the magnitude will increase, but negative hai wo. You're getting that? So actually it is decreasing. The potential energy of the system is decreasing. Negative mein badh raha hai, decrease ho raha hai. Is that clear now? So direction, even through electric dipole, these two electric dipoles which are having opposite orientation, that term is clear. So what is the direction we are getting? Attack kar rahe hain. पूछ लो. इसका जो E है वो दूर जाने पर डिक्रीज हो रहा है और नेगेटिव वहीं पर है, तो जो अट्रैक्शन है वो कम है, रेपल कर रहा है. They are repelling each other. Just observe by simple charges also or magnetic charges, whichever way you are comfortable. By Fx is equal to minus dou u by dou x also we are getting the same, they are repelling each other. So magnitude I have written, direction by logic I have written. Very simple, by charge plus minus also. Whichever way you are comfortable previously, you can use that. I think that is not a relevant thing. Repulsion is what we get. But the core idea of the problem was reciprocity. I will repeat the steps. It is a magnetic dipole which will have some flux to the bigger ring. To write the flux again, you have to use reciprocity. Once you get that flux, rate of change will give an induced EMF and current. That will generate a magnetic field. This magnetic field will have an interaction energy with the small dipole, and the rate of change of that magnetic energy or the magnetic interaction energy will generate a repulsion on the bar band. That is what is happening. So if an agent has to ensure that it keeps on moving rightward with a constant speed, he has to apply the same magnitude of force rightwards, because mutually they will repel. Calculation now you can do, right? That expression ka d by dx. Right. So now I'll finish off the class here. We'll pick up more combinations tomorrow. I'm deliberately, now decreasing the tempo. I am not taking those questions which are very complicated now, because just trying to, take you towards the JEE Advanced, because these will be the most relevant problems which you will directly find. So next week or from here onwards, you should try to solve as many problems, but it may not be the most typical ones, because the last week is not for solving the most typical problems. So that's why I've taken more objective, multiple correct, and not from the puzzling or the higher order books, which we have solved for the last 2.5 years. So there was a conscious decision by virtue of which I'm taking these problems. So more and more ideas. And these will be the kind of questions you will directly see in the examination. Majority problems. Barring one or two problems, which we think we have already solved in the last 2.5 years. Right. So fine. I'll see you tomorrow with more problems. Take care. Good night.